Welcome to our exploration of content-based recommendation system architecture. In this video, we'll explore the basics of machine learning, including the concept of featurization and model training. This will help you grasp the inner workings of a recommendation system. We'll then describe the overall architecture that can be deployed to generate recommendation using Azure services. We'll discuss the different data flows of the architecture and help you understand how the entire system operates. Whether you're a developer, an architect, or just someone curious to know how this architecture works, this video will provide you with valuable insights. My name is Madhur. Let's get started. Let's begin by setting the context. Recommendations are a key revenue driver for many businesses and are used in different industries including retail, news, and media. With machine learning, you can provide highly relevant recommendations to the customers based on their activity data. To understand the concept of machine learning, imagine you are teaching a curious student to identify different types of words. To achieve this, you show student pictures of various birds and point out the features such as beak shape, feather color, etc. that distinguish each type. Once the student has learned from enough examples, they should be able to identify the type of bird in a new picture they haven't seen before. In this analogy, the student is like a machine learning model, and the process of learning from the pictures is like the model training process. If this is very clear to you, let's understand the business problem and establish the requirements for the architecture. Our latest app, SpotiVibe, has been struggling with customer retention. The app has been recommending songs based on an external song ranking data source, but the drop rate after listening to the first song is nothing to brag about. To solve this, the team wants to upgrade their recommendation engine by using existing user and song data. Here are the requirements that they have outlined. The first requirement is to use existing user and song data to improve recommendations. Second, expose the results using API for their mobile apps and web apps to consume. The architecture diagram displays all Azure services and number data flows to be discussed. Azure Data Lake Storage stores large amounts of user behavior data. The dataset includes rows representing users. Columns include features like user listening history, song genres, artists, and other relevant information. Azure Data Lake Storage, or ADLS, is a cloud-based, massively scalable data storage solution specifically designed for big data analytics workloads. In the next step, Azure Databricks connects to and reads from Data Lake Storage. Ingestion into Databricks enables preprocessing and training to register the model. Azure Databricks is a cloud-based data analytics platform built on Apache Spark that enables collaborative data science, engineering, and business analytics. It offers fast setup, streamlined workflows, and integrated security within the Azure cloud environment. The third step is preprocessing. Data preprocessing cleanses, transforms, and prepares data to be fed to the recommendations system model. Next comes training. Training has two steps: feature engineering and model training. As part of feature engineering, you identify and modify data that will be fed to the model for training. Featurization is a key step within feature engineering. It involves transforming raw data into numerical or categorical features suitable for machine learning algorithms. I guess there's a lot of jargon here, so let's illustrate with an example. In the context of song recommendation, featurization involves transforming raw data about songs and users and creating new data columns or features. We know our dataset contains information about songs described by features like genre, artist, year of release, and user listening history. Using this, we want to build a model to recommend songs to the users. While these features can be used directly, we can create additional features to improve the model's recommendation accuracy. For example, there could be a new feature named genre category, where we can combine various subgenres like heavy metal, punk rock, etc. into a broader category called rock. By applying such featurization techniques, we transform the raw data into derived features that the machine learning model can use to learn. Once the features are prepared, the training data is ready to train the model. Model training equips a machine learning model with the ability to learn from song data and user preferences. This allows the model to predict and recommend songs likely to resonate with individual users. Post-processing involves model evaluation and selection based on which model performs the best. Here, Azure Databricks maintains the model. Patch-managed endpoints deploy the model for exposure to front-end display. As the model is deployed, the new data is accessible via new endpoints. Batch and near real-time recommendations are supported in this case. Whenever an end application hits the endpoint or API with the required parameters, the model is invoked and the results are written to and captured in Azure Synapse. User interfaces like web applications and mobile apps can consume the stored model results. Azure Synapse is a cloud-based analytics service that tightly integrates data warehousing and big data analytics. It gives you the power to query data across all your data stores using either serverless or provisioned resources, offering a unified experience for managing and analyzing large data sets. And there you have it. The solution is ideal for the retail industry. It's relevant to use cases like product recommendations for e-commerce sites, displayed ad recommendations for websites, and of course, recommendations for your next song, video, or movie. If you found this video insightful, don't forget to like, share, and subscribe. Until next time, stay curious, stay data-driven.